presumably this is for the recording. Right? Yes. The room is small enough that I can reach the room easily. Okay, how's that? Yeah, I can start whenever you're ready. Oh, this is amplified. Okay.
Sir, please let me introduce.
Sure.
Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IISc. It's my pleasure to introduce today's speaker, Professor Amit Chakrabarti. He will be speaking on designing robust algorithms for data streams that might be adversarially generated. Amit Chakrabarti is a professor in the Department of Computer Science at Dartmouth College. He holds a PhD in computer science from Princeton University and a BTech in computer science from IIT Bombay, where he was the President of India Gold Medalist. Professor Chakrabarti's research is in broad area of theoretical computer science, specifically in complexity theory, especially communication complexity, applications of information theory, and algorithms, including space-efficient algorithms for massive data streams and approximation techniques for optimization problems. He is particularly known as a pioneer of the concept of information complexity. The related work was awarded a 20-year Test of Time award by IEEE Symposium on Foundations of Computer Science. His research has been funded by several awards from US National Science Foundation, including a career award. Finally, we request all the audience to keep your microphones on silent for the entire duration of the talk, except when asking questions. And for questions, please feel free to unmute yourself and ask directly or type in the chat box. We will relay your questions. Over to you, Professor.
Well, thank you very much for introducing me. Thank you very much for inviting me here. Yes, it's a pleasure to be here. Some of you, most of you may not know this, but I grew up here, essentially on campus. My parents still live very close to campus. Visiting home, and it's lovely to be able to make an academic connection while I'm here. Thanks, Chandra, for making this happen. Okay, so I am, as you gathered, primarily a computer scientist. I have some connections with electrical engineering through applying information theory in my work. There isn't really any information theory in what I'll be saying today. However, the nature of the problems being considered I think should appeal to anybody who's interested in any flavor of data analysis. Okay, so I've tried to keep this talk broad and not really go into very much mathematical nitty-gritties. A different kind of talk could be given with full of mathematical proofs and algorithmic details. This is not that. This is trying to introduce you to this general area of research called robust algorithms for data streams. Okay, so there's a number of terms here which need to be defined. The term robust algorithms, the term data streams, which maybe you do know, but would be worth reintroducing, and then this thing about adversarially generated. Okay, so if you leave the talk understanding what these three terms mean, then I will consider myself as having succeeded. Okay, so first, data stream algorithms. They deal with algorithms where the input is to be thought of as evolving and very quickly evolving and involving lots and lots of data, more than can be reasonably stored and computed on offline. A classic example, I'm not sure if there's any action I can take that will slow down this thing, but a classic example is a network switch at a busy router, say, which handles billions of IP packets every hour, and if it's trying to keep any kind of statistics, such as how many distinct IP addresses have we seen over the past hour or day or week, then it will have to be algorithmically clever. It cannot simply store all the data and then just do offline processing. It's got to do other work, such as routing the packets. A key issue in designing algorithms in such a scenario is that you have to be space efficient. So each token or each IP packet comes, you analyze what you need to, you keep exactly what you need to, you update your internal data structures, and then the packet's gone. All of this has to happen very quickly because the next packet is going to come in a matter of milliseconds or even quicker. A different example comes from, say, systems like Google, which naturally handle large amounts of data, literally every hour, large amounts of data. And there's all sorts of statistics maintained in places like Google. This is just a simple example. You could go back in time and find out the trending searches in a particular year. You can zoom down even further. You can look for a particular date range, particular day, specific day, particular region of the world. So certainly, so you can ask, how is Google answering these questions quickly for you? It of course has the capability of storing literally everything it has seen, but it doesn't look at everything it has seen to answer a query like this. It's got clever data structures that enable it to quickly answer questions like this. What was particularly trending at a particular period of time? Behind all of these problems is, behind all of these systems is a few simple, clever algorithms that process data in sublinear space, where sublinear means a linear space would be, say I store only 1% of all the data I see, but that's still 1% of, if your data is of length n, that's 1% of n, that's still linear in n. These algorithms often store things that are only logarithmic or log squared in n. Okay? And soon we will start seeing some algorithms where this kind of sublinear space guarantees holds. Now, one key takeaway from this talk, in fact, this is going to be a recurring message throughout the talk, is that in order to design good algorithms in this situation or in these types of situations, in order to get sublinear space solutions, it is extremely important to use randomization, and you really have to harness the power of randomization. Okay, what does this mean? So let's take an example problem to illustrate what's going on. So I give you a stream of items. So there are m items, sequence like that, A1 through AN, and you see them in order. Each item is from a universe 1 up to n, and m and n are both extremely huge quantities. Right? Now you want to answer the question, how many distinct items are there in that sequence, or roughly how many distinct items are there. So some approximation will do. Okay, so I'll call this quantity dE for distinct elements of sigma. Okay, so there are two trivial ways to do it, but both these solutions are unacceptable. So let me just point out that one thing you can do, of course, is to store all the items. So you now have your entire sequence in memory, and then you do what you want. You can sort it, and then you can count the number of distinct items, say. Now this solution uses at least m amount of space, because there's m items, and you're planning to store all of them. This is unacceptable because m is huge. The other thing you can do is, instead of storing all the items, you can instead store a vector in n dimensions, just a 0, 1 vector, which says, have I seen item number I or not, yes or no. Okay, so this is also called a one-hot encoding of your data set. But that one-hot encoding uses at least n space, right? And n is also huge, so these are both unacceptable solutions. Now it turns out that there's a theorem you can prove that any deterministic method you use, notice that these methods are deterministic. There's no randomness there. That's gone, but hopefully you remember the two methods. They're deterministic. And the only randomness is in when exactly the slides will vanish. So, any deterministic solution that you try to use is going to require either m or n space. That's a theorem that you can prove. And therefore, if you want a sublinear space solution, you need to use randomness. Now, fortunately, there is a randomized algorithm. Actually, there are many randomized algorithms developed for this problem. It's a fundamental problem, as you can see. It's been studied for at least 30 years. Many people have developed algorithms for this, but culminating a long line of work, there is an algorithm that runs in this amount of space and provides a 1 plus or minus epsilon approximation. The important thing to observe here is that the dependence on n is logarithmic rather than linear. Okay, so that is an exponential improvement. Okay, both of these theorems are the result of some considerable amount of work. The first one started with a classic work of Alon Matias Segedi from now nearly 3 decades ago. And this form of the theorem is in a work of mine with a former student, Kale, also from a few years ago now. On the upper bound side, once again, the same paper presented an algorithm that achieves logarithmic space, but the overall dependence on the epsilon was not optimal. And this optimization came about through a bunch of subsequent works, and the ultimate result is from this paper. Right. So just to give you a sense that even for a simple problem like this, there's already a good bit of research work involved in getting the results that we have today. All right, so the lesson from all this is, without randomization, at least for this problem, you basically can't do anything. With randomization, you can do very, very well. Right? Okay, so randomness is powerful. Since the entire talk is going to involve randomized algorithms, I should clarify one thing, and apologies to anybody here who has been through a CS theory course. You know this very well, but if you haven't, this point is well worth making. We have to understand what exactly is random when I talk about randomized algorithms, okay? And what is not random is not the input. The input is not random. So you're given some data, you don't know anything about what distribution the data comes from. In fact, there is no assumption that the data comes from a distribution at all. Okay, it might be designed by somebody to be an especially hard data set. That's it. So the data is what it is. There's no randomness in it. What is random is the algorithm's decisions. So as the algorithm reads the data, it can use random bits, maybe by using a random generator, flipping a coin, whatever. And these random decisions will, be orchestrated in such a way as to work with high probability, right? So that is the nature of the algorithmic result you get. Okay, any questions on this point? Because this point really needs to be clear, right? It can cause much confusion otherwise. Now, there is a case to be made for dealing with data that is generated according to some distribution, Gaussian or Zipfian or whatever, but that's not what this talk is about. Yeah, sure. Yes.
So, if you say that there is a randomized algorithm that outputs an estimator,
yes.
Okay, then there is this probability of failure associated with it.
Yes. Yes.
But then the failure itself, the probability of failure has no influence on the space.
Okay, it does. I've kind of hidden it. There is a plus log 1 over delta in there, which I didn't write down. Yes, you're right. Yeah. So in fact, in reading this notation, think of this probability of failure as being an arbitrarily small constant. And if you don't like constant, the dependence on delta is what I said. There's a log 1 over delta. Yeah, but thank you for that. Yeah. Yeah, so somebody is reading my slides very carefully, and now I better be sure that I didn't make more mistakes. Okay. All right, so let me, I haven't actually shown you how randomness is used in that algorithm. I just told you there is a randomized algorithm. And unfortunately, that algorithm is a little complicated to explain quickly, but I can show you how randomness helps in a different situation, which is also a classic result in streaming. So let me show it to you. And this has relevance to something that I'm going to say about my work. So this is worth understanding. Okay, here's a different problem. I have a vector x in n dimensions. Again, think of n as being very high. And I want to estimate its length, like the L2 length, okay, Euclidean length. Now this vector changes as follows. It starts out being 0, and the stream consists of updates to this vector. So each stream update tells you, say, increase xi by an amount delta. So I give you the coordinate I and the amount delta, and what you have to do is increase xi by the amount delta, okay? Which can be positive or negative, so you can increase or decrease. Think of this as delta copies of item I being inserted into the stream, and if delta is negative, then some number of copies are being deleted from the stream. So in this way, you're maintaining a dynamic data set. Now, of course, you don't want to maintain the vector x itself because it's high dimensional. If you want to estimate the Euclidean length, it turns out, and this is reasonably well-known result from classic mathematics even, that if you sketch it by using a random sketch matrix, then you can project the vector down to d dimensions, for d being considerably smaller than n, so that the length of Sx is very close to the length of x. Okay? The classic proof of this uses Gaussian random variables for the matrix S, but Alon, Matias, and Segedi showed that you can just use random plus or minus ones to fill your matrix, and that'll do the trick. Okay, so there will be some scaling involved. So you have to take this vector and you have to take this length and scale it, and then you get the estimate of the length that you want. Okay, so that gives us a good streaming algorithm. Instead of n dimensions, you're storing only a d-dimensional vector. Now you can do the same with other notions of length besides Euclidean length. So for example, if you wanted to estimate the L1 norm, which is Manhattan distance, then a similar sketching type algorithm works, but the sketch matrix is different. You have to use entries that are IID from what is called a Cauchy distribution. Some of you may know what this is, but otherwise the algorithm is much the same. You maintain only the projected vector Sx, and to estimate the L1 length of the vector, you take the median entry in Sx. Okay? That's an algorithm due to Indic, also a classic at this point. Now notice that these algorithms end up using space only logarithmic in n. Okay, I didn't tell you that, but it's a theorem which you have to prove by doing a bit of analysis, that choosing dimension something like log n times some function of epsilon, it's log n over epsilon squared. So that's what it is. So choosing that dimension gives you these, gives you the property that this length is a good estimate of that length with high probability, and so on. Okay, so this kind of thing is called linear sketching. Instead of maintaining a vector, you maintain a linear projection of that vector in smaller dimension. Okay, so over the years, lots and lots of results have been obtained for data streams, and in fact, data stream algorithms is probably enough of an area at this point that you could write a thick textbook and not really cover all of the results. Just doing the basics will fill a thick textbook. That textbook hasn't yet been written, unfortunately. I have an attempt on my webpage, but it's more of lecture notes than a textbook. Still, if anybody wants to know more about this area, then please look at my webpage. I do have lecture notes for a course that I teach, which at least has the basic results from data stream algorithms, including details of the two that I just showed you. The area began sometime in the late 70s with a classic work on finding medians and other order statistics. Then in the early 80s, there was a result by Misra and Grease on finding high frequency items in a stream. And then it wasn't really researched in a big way until this paper of Alon, Matias, and Segeri that I've referred to a few times. If you ask people today, they would say this is where the area really started. So this is a real landmark paper. And there are so many ideas in this paper. This paper is so brimming with ideas that pursuing the open questions raised by this paper occupied researchers over the next 15 years or so. Now it's been pretty well hashed out, but that's really where the modern history starts. There are algorithms for various statistical problems. There are algorithms for graph problems. There are algorithms for geometric problems. So many different things have been considered in data streams, and I haven't even mentioned all the different possibilities here. There are algorithms for string problems that I haven't put on the slide. Okay, so that's basically the nature of the area. Besides designing algorithms, the other major research project in data streams is to prove lower bounds, saying that so and so is not possible. Or if you wanted an algorithm for this problem, then you must use at least this much space. So that type of result is called a lower bound. I showed you one already when I said deterministic algorithms for the distinct elements problem require a lot of space, right? Okay, so later as I talk about my work in this talk, then there will be a little bit of algorithmic work and a little bit of lower bound work as well. Okay, so that's what it is. Okay, let's talk about adversarially robust. So hopefully everybody understands what data stream algorithms are and what the central goals are in designing these algorithms. So what is this thing about adversarially robust? Now this is a relatively new paradigm in data streams. Okay, so if you look back at the history, that's how far back the history of data streams goes. This only goes back about 4 years. So 2020, at the start of the COVID era, was when a couple of papers really kickstarted this area, which I'm now going to introduce to you. So data streaming algorithms are deployed in many systems. I've already made this point. So let's think of one particular way in which you might deploy data streaming algorithms. The world, that is us, when we interact with various systems, we generate data. For example, when we watch, say, movies on streaming service, that generates viewership trends. So there's a sense of which movies are popular today, or what's rising in popularity, what's decreasing, what new movies have come out, what might be popular with what demographic, and so on and so forth. All of this is data generated by people, say, watching movies, TV shows, whatever, online, okay? And streaming services collect this data, of course, and they use it to make movie recommendations, right? So when you go to any kind of streaming service, Netflix or whatever, it will tell you that these things are recommended for you, and it does this by its own internal analysis methods. Okay, so there's streaming algorithms deployed to do things like this. Now, based on the recommendations you receive, you may choose to watch this or that next movie or show or whatever, and therefore these results affect the world, right? So the world generates data based on which you receive recommendations, based on which you generate more data, and this creates a certain feedback loop. So the outputs of these streaming algorithms are getting fed back into future inputs to the algorithms. That makes sense? Now, once you have this feedback loop, then the algorithm designer's task becomes more complex because he's now playing against this kind of feedback loop, which it's not clear what its behavior is going to be. Okay? In the worst case, this behavior could be adversarial. All right, so just imagine the following behavior. You've designed an algorithm which is space bounded and is supposed to do something with your data stream, right? Maybe it sketches your data stream at each point of time. So a data stream consists of a sequence of items or tokens. And if you think of these tokens as being generated by this adversary is able to do the following now because of the feedback loop. Supply a token, okay, start off your data stream, let the algorithm run, it produces some results. Based on the results, the adversary can now plan, here's what I'm going to do next, here's how I'm going to continue the stream, so that the task becomes hard for the algorithm, or the algorithm has a higher probability of making a mistake. Okay, and it gets some more results, and then the adversary gets to generate some more tokens, and so on and so forth. See, this is different from the situation before where we were saying, maybe you designed a data stream algorithm that works for worst case data, but that worst case data is going to be produced by an adversary before your algorithm starts running. Okay, so you allow the adversary to do their worst, but once they've said this is the input, now your algorithm runs on that input, and it has whatever guarantees it has. What the adversary doesn't get to do is to see your algorithm running for a while and then say, oh, actually, I want to change the hard input. It should continue as follows, right? But now the adversary can do that because of this feedback loop. Because the outputs of the algorithm affect future inputs to the algorithm, the adversary gets to do this. If you can design your algorithm so that despite this adversarial interaction, it still works well, then we say that the algorithm is adversarially robust. Okay. So up until 2020 or so, all of the algorithms that were being designed weren't designed with this scenario in mind. So they may or may not be robust. So let me make now two observations. Actually, one is a theorem, which requires a paper to prove. The other is a straightforward observation. The straightforward observation is that if your algorithm is deterministic, then it is automatically adversarially robust because an adversary has nothing to gain by interacting with the algorithm, right? An adversary can just pretend execute your deterministic algorithm itself. So it already knows what outputs you will give in response to whatever inputs. Okay, so there's nothing unpredictable to an adversary. Okay, so deterministic things are robust. Of course, unfortunately, as you have seen, deterministic algorithms typically don't exist for interesting problems, right? So the fact that deterministic algorithms are robust isn't very helpful. Now, a theorem that we have is that problem of estimating Euclidean length that I talked about earlier. We had a solution using linear sketching. I told you a particular kind of sketch will solve the problem for you. There's a theorem that says any linear sketch you use will fail to be adversarially robust. So if an adversary is going to interact with such an algorithm, then it can cleverly probe the algorithm and learn too much about the sketching matrix S and then cause the algorithm to err with high probability. So if you give the adversary this power of interacting with the algorithm, then you're toast. So the linear sketch solution doesn't work. Okay, so like I said, so that result was from 2013, and they weren't really thinking about adversarially robust algorithms then. They were just looking at that one particular problem, and they made this very nice finding, and it kind of lay there. But in 2020, two different teams of researchers started thinking about this scenario I just showed you. They went back to that Hart-Woodruff result and said, oh yeah, so it is known that in some situations, some algorithms aren't robust. Can we make algorithms robust? Is there some general method maybe to turn a non-robust algorithm into a robust one, possibly by adding some extra stuff to it? Okay, so we do know so far that for certain families of problems, and the important thing is that there must be no item deletion. So if a stream consists of only adding items to a data set but never removing, then there are pretty large families of problems for which you can take an existing algorithm and then make them robust by using a simple technique which I'll describe next. Okay. There are some problem-specific solutions as well, but these are a bit more ad hoc. Yeah. Now, once we start allowing deletions, we actually don't know any efficient solutions, even for some basic problems like this Euclidean length problem, right? And in a few cases, for a handful of problems, we do have lower bounds which rule out solutions that are too efficient. So that's the state of play. We don't know a whole lot. There are maybe 10-ish interesting results between 2020 and now that potentially could be presented for the rest of the talk. But of course, this is my talk, so I'm going to focus on a couple of mine, right? So what I say next, please don't take what I say next as being the most important things about robust algorithms. It's the part of robust algorithms that I have worked on. Yes, go ahead. Yeah. Yes. Yes. Which would rule out a too efficient solution. Yeah, I mean, that's what a lower bound is, right? It's saying that if you want robustness, then your space usage cannot be less than so and so. Equivalently, your space usage is greater than or equal to so and so. That's just a lower limit, saying that you must use at least this much space in order to robustly solve a certain problem. Yeah, I'm just spelling out what a lower bound is. Yeah. We already have lower bounds. We have lots of lower bounds in the non-robust case. In the robust case, there's just a few at this point. I mean, obviously, any non-robust lower bound applies, right? A robust algorithm, we are asking more of the algorithm when we want a robust algorithm. So any lower bound that exists in the non-robust case will continue to apply, of course. When I say this, I mean that there's a few problems where we can show that robust algorithms require even more resources than non-robust ones. One would suspect that is often the case, but there's only a few places where we know how to prove that. Okay, so in this talk, I will say a little about graph coloring on the upper bound side, and I will say a little about this missing item finding problem. If you looked at my abstract, you will see it mentioned on the lower bound side. Okay, so I will introduce both these problems and just say a little about the state of play. Okay, that's the plan for the rest of the time. Yeah, perfect. Okay, so to start talking about this, let me show you one of these promised robustification techniques. So the situation is you have an algorithm, a good efficient streaming algorithm for a certain problem, and you want to turn this into a efficient robust algorithm. Yeah? So how do you do this? So let's say the small space algorithm that you currently have is A. So A is not robust. So I'm going to make a new robust algorithm out of A. So I'm going to do this by running several independent copies of A. Okay, so lambda of them. What is lambda? I'm going to explain in a minute. But I'm going to run several copies of them, and I'm going to run them in the following manner. So up here, the top bar, this I really need the picture for. Okay, stay steady for a minute. So as the input stream progresses, all copies of A will process that input stream, except that the first copy will stop at some point and not process it any further. The second copy will keep processing. It will stop at some point. And then the third, and right now the third, fourth, and fifth copy are all processing the stream exactly as given. All right. So there's a certain logic for stopping a certain copy and transitioning to the next copy. So the algorithm has a notion of its current copy, right? Okay. So now let me show you what the logic is. So we're maintaining basically two things. And besides running all these copies of A, we're maintaining two things. We're going to maintain the most recently reported result, right? Now, I didn't tell you what this algorithm is for, and in a sense, you shouldn't worry about that. This algorithm is for computing a certain function of its input. Never mind what that function is, but there is a correct answer, and any good enough approximation to that correct answer will do. So anytime you're reporting an output, saying, for example, this is the number of distinct elements in the stream, okay, just to run with the first example I did. An approximation will do, so let's say res is the actual result that you have reported. So this is an approximation to whatever function is being computed. We'll also maintain the index of the current copy of the algorithm, which in this case would be 3, I guess, because our current copy is A3. Right. So each time we read a new item in the stream, so each time the stream grows, of course, the old copies don't do anything, they're dormant. We feed this stream item to all of the copies that are still running, and we check the following thing. So we check if after a new item has been added to the stream, this result is still a valid result or not. For example, if we were reporting an approximate number of distinct elements, then maybe after seeing a new item, the number of distinct elements has changed a bit too much, and the old result is no longer a good approximation, then we need to give an updated result. If this is not the case, if the old result is still good, then we continue to report the old result. Now think of the adversary. The adversary basically learns nothing new because we are still reporting the old result, right? However, if the result needs to change because it's not valid, then we're going to say we'll move the current copy to be the next one. Okay, so we're going to stop this particular run of the algorithm, and we'll move the current pointer to the next copy of A, and we'll only update the future ones from now on, right? If we had to update the current copy, then we recompute a new result. So the point of the scheme is to give new information to the adversary only rarely. So we only give new information to the adversary when the underlying result changes by a bit too much that we can't just reuse our old result. Okay, so if the nature of the problem is such that the result that we need to report cannot change too many times by a large amount, then this scheme works well. And a lot of problems do behave this way. So if you think of items being added to a set and only being added, not deleted, so that the number of distinct elements can only keep increasing monotonically, then you can compute how many times can this possibly be changing by more than, say, 1 plus epsilon factor. Okay, it's not that much. It's logarithmic in the entire range, right? So this number, maximum number of times that the output can change by a lot, is called the flip number associated with the problem. If this flip number is small, then the scheme works well. So lambda is the flip number. Okay? So the flip number depends on what problem is being solved by the algorithm. Good. So this makes sense. If the old algorithm A used a small amount of space, the new algorithm uses lambda times that amount of space because we're running lambda copies of the algorithm. If lambda is small, we're good. Yeah.
How do you validate this then?
Validate what?
How do you say whether the result is valid or not?
Oh, this is, okay. So the algorithm can compute whatever the new result is, right, by actually running this copy of the algorithm. So there is a result that is the proper result that this copy of the algorithm would have reported after the change. Okay. If that new result is not too different from the old result, as in it differs by at most a 1 plus epsilon factor, then we don't actually report the new result. So the algorithm is computing what would have been the ideal result, but it's hiding it from the adversary by not outputting it. So you only output your previous result, and you keep it. You keep outputting that previous result as long as it's not stale. Yeah. You always know what is the correct result you should be outputting ideally, but if it isn't that different from the old result, you just don't report the new result. Yeah. Yeah.
So this randomized algorithm is maintaining the old result.
Yeah.
But that is outputted by the algorithm. So this randomized algorithm, we want the result output by the algorithm not to differ by an epsilon factor from the actual result, right?
From the last reported result. So the point is we are computing an approximation, right? So it's not like there's only one correct answer. Well, I mean, there is one accurate value, but there's a range of values which are all valid results because they're within the approximation range, right? So long as you compute your approximation and you're sure that you're not out of the correct approximation range, you keep reporting the old result. Yeah.
But this updates when the current result is out of the approximation range of the old result, not the accurate result.
Okay, good. Yes, so good. Yes, you have caught on to some other little bit of cheating that I've done here. The fact is that a 1 plus epsilon approximation of a 1 plus epsilon approximation is a 1 plus 2 epsilon approximation. So you can use this fact. Yes, good. Yes, you're absolutely right that the algorithm never knows what the actual accurate answer is because it's a streaming algorithm with low space. It only knows an approximation, but what it's outputting is guaranteed to be a good enough approximation to that good enough approximation. So yeah. So true. So where I mean, I guess I didn't ultimately state what the approximation guarantee of the overall scheme is, and it's going to be 1 plus 2 epsilon for the reason that you said. Yeah. Okay, good. So this is one generic technique for robustifying an existing algorithm. There are two other generic techniques that have been developed, which I won't go into, but the technique that I just described is called sketch switching. This was developed in 20 by these guys. Another technique also developed in 20 uses a notion of differential privacy. It's very interesting. People heard of differential privacy? And it's a reasonably popular term these days. Apple advertises that our systems use differential privacy. I don't know what to make of that, but anyway. So But yes, but it's a legit technique for hiding information from people, and since the algorithms in this case need to hide information from the adversary, it stands to reason that the ideas may be useful, and indeed they are. And then there is another technique invented a bit more recently. But anyway, I won't go into all this. I'm just saying that there are other results that are in this vein, of turning a non-robust algorithm into robust.
What is the intuition behind having multiple copies and then providing robustness?
Yeah, so the idea of the multiple copies, I guess, is that yeah, good, maybe the picture is useful. See, it's called sketch switching because what we are doing is we are so it's like these are all different sketches of the data. So each copy of the algorithm is a fresh sketch of the data, right? Using new randomness. Okay, I guess that was unsaid, but we use completely fresh random bits here. So the results of this copy are independent in the sense of random variables from the results of the previous copies. Okay, so the thing is, if each time, let's take an extreme case where every time you're asked to give an output, you're able to use a fresh sketch to give the output. Then the adversary is helpless because anything he has learned in the past from your outputs is independent of the randomness you're going to use to compute the new output. So learning the randomness used by the algorithm is useless for the adversary because all the randomness used in the past is not going to be used for future outputs. So this is sort of in between. So in that extreme case, you'd have so many copies of the sketch that it would no longer be space efficient. But now you have, this is a mechanism to make sure that with just a few copies of the sketch, you have a clever switching mechanism which ensures that your adversary just fails to learn enough. So anytime there is a danger that you're revealing too much information to your adversary because you'll be giving a new output from the same sketch that you're using to compute the old output, then you don't do this. You say, okay, this sketch is dead. Let's move on to the new one. Yeah. Okay. So then, good. So then let me talk about the two problems, finally coming to sort of the new results of mine. This is all setting the stage, but I've given you a bunch of useful things by way of background. So there's linear sketching, which we talked about. There's sketch switching, which we talked about. So now let's actually talk about the problems where I have some recent results. So one has to do with graph coloring. Are people in general aware of graph coloring? People know about, say, the 4-color theorem, for example, a famous result about graph coloring. Okay, so that's the kind of coloring we're talking about. We have a graph. This is a streaming algorithm, therefore the input is not given all at once. The edges arrive in a stream one by one. So let's say the nodes are fixed, they're known. So the nodes are numbered 1, 2 up to n, and the edges are what constitute the stream. Okay, so the stream consists of, okay, here's an edge, then here's an edge, here's an edge, and so on. Good example of this might be that you're running a network with a known set of users, you're running Facebook or something like that, and the edges can correspond to some two users having a certain interaction, right? It's like one person commenting on the other person's wall or just liking some post of theirs or something like this, okay? So that's the kind of thing that could be evolving. Okay, so the coloring problem is assign a color to the vertices, assign a color to each vertex so that two adjacent vertices don't get the same color, right? So anytime there's an edge, you must have different colors at the endpoints. Now you want to use as small a palette as possible. If you can color the graph with the fewest number of colors, then you would have fully solved the graph coloring problem. This is a very hard problem. This is, in the parlance of computer science, it's an NP hard problem. It is in fact harder than NP hard. It is what is called APX hard. It's hard to get any kind of approximation to this problem. So extremely hard problem computationally. Now, the version of the problem that I'm going to talk about is not that very hard one, where we have to find the minimum possible number of colors. Instead, I'm going to say the graph is known to have a maximum degree of delta. So there's some parameter delta that's known to us. And all I want is a coloring using delta plus 1 colors. Okay, so is this going to work? I know this is not going to show up on Zoom. I'm sorry, but I'm just going to do a quick little thing here to say, how do you color a graph with delta plus 1 colors? I claim that this can always be done, and it can be done very simply. So you can just use a greedy method to say, start coloring the vertices one at a time in any way you want, okay? And when you consider a particular vertex, so let's say all of these vertices have been colored, or maybe some of these vertices have been colored, and you now want to assign a color to this vertex. right? How do you color it? So let's say maybe here the color 2 has been used, the color 1 is used, the color 4 is used, and this is not yet colored. Let's say this is the situation you're in. It's now time to assign a color to this vertex. It has to be different from all the neighbors' colors. You have a palette of size delta plus 1. The degree of this vertex is at most delta. It's guaranteed there's going to be a free color, right? So whatever color is free, pick any one free color and assign it here. So you can just keep doing this. So there's a guarantee that you'll always be able to color the graph with delta plus 1 colors. And in fact, the algorithm is very simple, just a greedy algorithm, right? Of course, the trouble is if the graph is given as a stream, then you can't actually run that greedy algorithm. You don't have all these edges in front of you. So you can't answer this question of which color is free for this vertex. All right, so that's why it's an interesting problem in streaming. Okay, so is it possible to find a delta plus 1 coloring in a streaming fashion using sublinear space? Okay, so this is sublinear, right? N times delta is the space required to store the graph because with n vertices, maximum degree is delta. So little o of n delta means sublinear in this quantity. Okay, so what can be done? So here's something that can be done. First thing is to take note of what kind of space bound can we even hope to shoot for. Okay, so log n is too good in this case because we have to produce a color for each of n vertices. So simply to write down a color for each of n vertices is going to take at least n bits. In fact, it's going to take like n log n bits roughly. Okay, so just information theoretically, you cannot hope to use space that's less than n log n. Now it turns out that you can do interesting things in space that is slightly more. So it's n times, well, I'm saying poly, it's log cube. So the polynomial here is cubic. So in n times log cube n space, so a few years back, so again, this is me with a couple of other students, we showed that you can get a coloring that's not 1 plus delta, but 1 plus little o of 1 times delta. So you get close, but you're not all the way there. And then Asadi, Chen, and Khanna, so you might wonder about this result is stronger than that result. How come it's earlier? Well, it's not really earlier, but you know, it's the way publication histories work. So Asadi, Chen, and Khanna showed this really landmark result that you can actually get a delta plus 1 coloring, right? The same thing that you could have done with a greedy algorithm can be done in streaming fashion in a space efficient manner. So for this, they designed a sketch called a palette sparsification sketch, or PSS, which I will briefly describe next because it's relevant to our work. Anyway, these algorithms are not robust. Okay, so they are meant for a graph that is just fixed in advance, possibly by an adversary, but it's fixed in advance, right? So if the adversary gets to add the edges to the graph based on the past colorings, so this means the adversary gives you a few edges and says, color this graph for me, you color it, and then the adversary says, okay, now I'm going to add these other edges based on your coloring, specifically to foil you. If you do that, then these results are not valid anymore, but here's what we can prove. So in space that is, this is sublinear, this is instead of n times delta, it's n times square root delta. So in sublinear space, we can show how to maintain a delta squared coloring. So not delta plus 1, but delta squared, right? And in space that's comparable to this space, we can get a delta to the 2.5 coloring, slightly worse, but the space is the same as that. Okay, so this is a relatively new result. And just a very brief outline of how this is done is, okay, so I have to tell you a little something about how palette sparsification works. So palette sparsification works as follows. For every vertex, before we see any input, okay, we know the vertices in advance. So it's like maybe it's the set of all users of Facebook or something like that, or the set of integers from 1 up to n. For every vertex, we choose a random list of colors from the available list of colors. So the available list of colors is say 1 up to delta plus 1, right? So we have to use these colors to color the vertices. So from the available list, we choose a sublist of size log n, right? Order log n. Okay, so now each vertex has its list. Okay. Now as we read the edges in the stream, when an edge comes in, we are only going to retain the edge if the two corresponding lists intersect. For example, these two lists do not intersect. So if this edge were to arrive in the stream, we will just not store it, we'll just throw it away, right? In this way, we store only a small fraction of all the edges that we see in the stream, and it can be proved, not a very hard argument, it's a straight up probability calculation, that the expected number of edges we store is low. It's like n times log n roughly. Okay, Good. So the net result is we have now retained only a small fraction of the original graph, so we're being space efficient. But we have to produce a coloring. So in the end, we're going to produce a coloring by giving each vertex a color only from its list. So then you can see that there's no danger in discarding this edge. See, this list and that list don't intersect. So I don't care if these vertices are adjacent or not. Anyway, I'm not going to give them the same color because their lists don't intersect. Right? So the only edges that are in danger are ones where the lists intersect. And those vertices might end up getting the same color. Therefore, I retain those edges. Now, having retained those edges and having kept those lists, one has to now come up with an algorithm to offline color this small retained graph subject to those lists. It is not at all clear that this is possible, and this is a deep combinatorial lemma that showing that this is actually possible. Okay. Anyhow, so that's how PSS works. Now, in our robust algorithm, we're going to combine this technique of PSS with the technique of sketch switching and another technique, simple technique of chunking. Okay, so what does this mean? So this is roughly how the algorithm works. This is all I will have to say about the algorithm. I'm not doing any proofs in this talk, so this is just to give you a shape of the algorithm, and I'll leave it at that. So as the input comes in, I'm going to chunk the edges. So the input consists of edges of the graph, right? So I'm going to chunk the edges in little chunks or batches. So each batch will have size n times root delta. So as a chunk comes in, I store all the edges in this chunk. So it's completely stored, right? So as the stream progresses and when I move over from one chunk to the next, obviously I can't retain every edge throughout because otherwise I'm not being space efficient. So at this point, when I'm at the boundary between chunks, I'm going to say, I'll take this portion of the graph and apply a palette spacification sketch to it, and therefore reduce it to a much smaller graph. So that's all I will retain about the first chunk. As I'm reading the second chunk, all I remember about the first chunk is that sketch of the first chunk. After reading the first two chunks, I will only have the sketches for the first two chunks, and so on and so forth. So in general, there will be a current chunk, which I will have stored completely in a buffer, but for all previous chunks, I only have their sketches. And this information suffices to compute a good coloring, because from each PSS sketch, I will compute a coloring as indicated over here. And based on the colorings induced by the previous portion of the graph and the current portion of the graph, I can compute an overall coloring that's good with respect to these edges plus those edges. So being good with respect to this and that is what causes this delta number of colors to shoot up to delta squared. So this is an algorithm that gets you the first of the results. Okay, so I don't have that written on the slide, but I'll just show you once more. Yeah, this result. So what I just showed you gives you this first result. So n root delta space because that's the size of a chunk, and then delta squared colors because, well, you have to combine two colorings. Yeah.
You want to sample log n random colors.
Yes.
So delta should be sort of bigger than log n.
Yes. Good. So let's go back to the kind of space bound I'm shooting for. So the space bound I'm shooting for is something like n times polylog n, right? So if delta is only log n, then the problem is too easy. I just store the whole graph, and that's only n log n space. So yeah, so the problem itself becomes non-trivial only when delta is substantially larger. So it's worth thinking of delta as being n to the power 0.1 or 0.2 or something like that. So it's that kind of size. Yeah. Good. That's a good question. Thanks. Yeah. Okay, so I just showed you that first result. In the beginning of this talk, I told you that one important message is going to be about how randomness is powerful. And one message I want to give you with regard to all these results is that you can make a more subtle statement than that randomness is powerful. Different kinds of randomness have different kinds of power. Okay, so I want to get this message across, so let me get there slowly. The other result we can show, haven't said anything about how to do it, is that you can get the space down to n polylog n at the cost of increasing these colors. But this algorithm has a certain caveat to it. This algorithm requires the use of a very long random string that it has to consult from time to time. How long? In fact, it is omega n times delta bits. So remember, n times delta is the size of the input. So this algorithm requires a source of randomness that is at least as big as the input. Now some may object to that, saying that the whole point is to use space less than n delta. So how is it okay to use a random string that's that long? So I would say that, well, you can say two things. One is that, okay, that's read-only randomness. That's not processing space. That's just a random string that's out there. Okay. So maybe I can say, okay, allow me that freedom. So I'm asking you to allow me to weaken the model like that. maybe strengthen the model is the right word. So yeah, so that's the thing. So the algorithm doesn't need to store this, so they're free. But then that becomes a model definition issue. So are you okay with a model that's defined in this way, that random bits are free? Okay? It's only your computation space that counts. Some would say, yeah, okay, fine. Some would say, no, that's impractical. All right. So I have an answer to this impracticality, which is that there is an algorithm that does not use this kind of randomness. So this is referred to as a random oracle. So an algorithm that just uses a free source of randomness is said to be using a random oracle. But it is possible to give an algorithm that doesn't use a random oracle, but the number of colors goes up some more. So I don't know if you, yeah, if the slide stays for a while, this goes up to delta cube, okay, instead of delta 2.5. Okay, so you could also ask that in the non-robust setting, we were able to get the number of colors all the way down to delta plus 1, right? Can we get delta plus 1 over here? So here we're only getting delta squared, delta cube, and things like that. So the answer is no. If you must use n polylog n space, then you can prove, in an adversarially robust fashion, you can prove that you need delta squared colors. Okay? So that's also a result of ours in the same paper. Okay, I don't have any time to talk about how the lower bound works, so I'm just telling you that it can be done. I'm happy to talk to you offline if you want to know. That part actually does use some information theory, so yeah. Okay. So this point I want to make about different forms of randomness. So we've seen now 2 different forms of randomness. So okay, maybe 3 different forms. There's determinism, which is no randomness at all. Then there's random oracle, which says randomness is all free. You can use as many random bits as you like. And then there's this in-between thing which says randomness can be used, but it's not free, and you have to store any random bits that you intend to use. Okay, which is probably the most practical model. Let me point out that back when I showed you this linear sketching using random sketch matrices, I actually pulled a fast one on you, and I was actually using a random oracle there. You may not have noticed, maybe you did, but the fact is that the sketch matrix S has to be stored somewhere so that you can compute S times X, right? So even though the dimension of the sketch is small, somewhere S has to get stored. What about the cost of storing S? So here you can say, yes, if you use a random oracle model, there is no cost to storing S because randomness is free. That's maybe not a satisfactory answer. Fortunately, there is a more satisfactory answer. For these particular problems, using a technique that is, okay, that will require a separate talk to explain fully, but there are techniques which allow you to generate this sketch matrix S on the fly from a much shorter random seed. Okay, so you don't actually need to store the matrix S, you store something else from which you can generate columns of S on demand. Okay, so that's how these algorithms really work. Okay, so this introduces this other kind of randomness, which is random seed. Okay. Okay, so there's a couple of central philosophical questions being raised here. So is it the case that random oracle algorithms are more powerful than, say, random seed algorithms? Now, this little example here shows you that what used to be a random oracle algorithm has been turned into a random seed algorithm, or can be turned into a random seed algorithm. So this is an example of not showing you that random oracle is actually more powerful. Okay? But is there a case where random oracle truly gives you more power than random seed? That's question 1. Question 2 is, even if you use this practical kind of randomness, there's 2 different ways to think about randomness. One is the seed kind. So a random seed algorithm uses its randomness in the beginning. On the other hand, there are sampling algorithms throughout streaming. Sampling is a common technique. So as the stream comes in, you choose to retain certain elements or not. So sampling type algorithms use a slightly more powerful notion of randomness than random seed. Okay, so can you prove that sampling type algorithms are more powerful than sketching type ones? Okay, now to begin to answer these questions, you need definitions. All right, so I will actually define. If you've been keeping count, I've now defined 4 kinds of randomness. So there's really 5 kinds. So let me just spell them out for you. Okay, these are not precise mathematical definitions, but they're just outlines. Okay, of what these quantities are. Okay, so there's deterministic. Nothing more to say about that. Now there's a notion called pseudo-deterministic, which says that your algorithm can use randomness, but with let's say 99% of the time, it must give one fixed answer, just as a deterministic algorithm would. See, a deterministic algorithm will always give a fixed answer to an input. Right? So if you use randomness, but you must give a fixed answer with high probability, that's called pseudo-deterministic. Yeah. Okay, more general than this is a random seed algorithm, which is the kind that I was talking about before, which is before the input stream is seen, you make certain random decisions. And then the rest of the algorithm is deterministic, but you can consult those random decisions in the beginning. So the net effect is to have a randomized algorithm, right? Now, quite a lot of data stream algorithms work that way, random seed. Okay, so that is a pretty powerful model already. But you can be more powerful, and you can use what is called a random tape, or at least what we call a random tape algorithm, which is as the stream comes along, as you read each item in the stream, you can toss fresh random coins. Okay, so you can keep using randomness again and again as you read the stream. And then finally, there's random oracle, which says no randomness has to be stored anywhere. There's just an essentially infinite pool of randomness available to you to dip into whenever you want. Okay. So I'm about to enter the very last bit of the talk. If you get lost in some details in this very last bit, let me just tell you that the takeaway is that all of these can be shown to be different from one another, right? And this can all be done by using one single example problem. Okay, so these are just pictures of what I was showing you. Yeah. Okay, no randomness. There's some randomness in the beginning, but the rest of the algorithm is deterministic. Here, this in random tape, along with each input item, you have random coins which you can use, and then random oracle. The randomness is sort of up there and doesn't even count towards your space usage, right? It's just a picture of the same thing. Okay, so here is a problem. This is a toy problem, but the point of this toy problem is to, I mean, maybe it's interesting in its own right, but the point of the toy problem is to show you that these different forms of randomness are actually different from one another in power. Okay, the toy problem is, it's called missing item finding, MIF. You have a universe, 1 up to n. You have a stream of up to L items, length L at most. And think of L as being quite a bit smaller than n, okay? So the universe is big, the stream is much smaller than the universe. Okay, the goal is at each point of time, you have to output an item that's missing in the stream so far. So yi must not be in x1 up to xi. Okay? So each time report to me a fresh item that hasn't been seen so far. So that's it, just report a missing item. Okay, so this whole thing, of course, the stream could be generated by an adversary. So the adversary might see what items you have reported as missing so far, and based on that, they can give you new items for the stream. Okay, so we want a small probability of error over the lifetime of this algorithm, say. Okay? A polynomially small error like that. Okay, now before you worry at all about adversarial robustness, let's ask ourselves two questions. What is the randomized complexity of this problem, and what is the deterministic complexity of this problem? So it's a bit late in the talk for me to really ask you what do you think is a good algorithm and just have you come up with an answer, but just still, anybody can think of an obvious idea? Okay, one obvious idea is just report a number at random and hope that it's missing, because that won't work because the error level has been set small enough for that not to be a good algorithm. You can do something slightly better, which is to pre-decide on a random set and just say, I will just keep track of whether this particular random set of items have been hit or not. If the input, anytime the input stream hits one of the elements in the random set, I'll cross it off. Anything that hasn't been crossed off is still a missing item and I can report it, all right? So if you just do the calculations for this idea, then it gives you a space bound of log of 1 over the error, which is say log n. Okay, so in log n space, you can solve this problem. Of course, this is not robust at all, okay? So this is assuming it's a kind of a static adversary. In the deterministic case, there's no obvious idea. Lacking an obvious idea, you might think that this requires L amount of space, okay, or maybe L plus 1. So you can do it with L plus 1 by keeping, say, a one-hot encoding of the first L plus 1 items in the universe, and then cross things off as they become, as they appear in the stream. So anything that hasn't been crossed off is a missing item. So that would be L plus 1 bits. You can actually improve on this L, and you can get something that is slightly sublinear in L, okay? And it is good to note this. So this hints at some kind of mathematical depth in this problem. The problem is not a completely mathematically dull problem, right? So something non-trivial is possible algorithmically. That's nice. Anyway, so like I said, by just studying this one problem, MIF, in the different models, random oracle, random tape, random seed, etc., we have different space bounds for this problem. So this is just a table of results to show you we can in fact analyze the space complexity of this simple problem fairly thoroughly in all these models. You will see that the upper and lower bounds essentially match. There is a tilde on top of these O's. This tilde notation, I apologize on behalf of all computer scientists for this slightly clunky notation, but it is commonly used in computer science to suppress logarithmic factors. So there's that, maybe there's a times log n in some of these results. Okay. It's hard to stare at results like that and see what it's really saying. So let me try to explain it in two ways. One is by showing you that there are 3 exponential separations in this table by setting L to be appropriate, right? So L is the length of the stream. As a function of the size of the universe, if it's n to the 2/3, then this separation shows you that in a non-robust setting, we have an upper bound of log n. In a robust setting, our corresponding lower bound is polynomial in n. Therefore, this is an exponential separation. At this level of L, we see that between random oracle and random tape, we have an exponential separation. Yeah, these are all just a matter of plugging in and doing the algebra. If you plug in n to the 1/3 into here, you end up with see n to the 2/3 over n, which is less than 1, right? So this upper bound goes away. The problem becomes only logarithmic space, but the lower bound is still, it hasn't gone away yet. Okay, so this shows that random tape algorithms are less powerful than random oracle algorithms. I mean, that's what you would expect intuitively, but now we can prove it. And then finally setting L to be this quantity. So this is sub-polynomial, right? Sub-polynomial, but super logarithmic. Now we see a gap between random tape and random seed algorithms. So all these separations are exponential. Okay, very good. Here's the same result shown in graph form, if you prefer that. So this is a log-log graph. So differences in slopes are basically different exponents of n. And the quick takeaway from this graph is that we have, so in the different colors indicate different models of randomness. This graph shows both the upper bound and the lower bound curve. So you see the curves match, so there's no gap region. This is what I believe the term of art in EE is inner and outer bounds. So yeah, so when I say upper and lower bounds, just think of that in your mind. All right, so this is the one place where we don't have the tight relation. So the best upper bound we have is slightly larger. The best upper bound we have is slightly larger than the best lower bound. Okay, so if you want to close off a gap here, then if you want to work hard on this particular problem and close it off, that's an open question. Okay, talking of open questions, let me finish with a couple of pretty broad open questions here. There's the nitty-gritty ones, which is that you can go back to our table of results and try to close the gaps, but the broad ones are more interesting. So estimating norms, estimating Euclidean length too, if you want to take a concrete example. As far as we can tell, once your stream has both insertions and deletions, this is a hard problem. Okay? When you have only insertions, the sketch switching technique works. When you have both insertions and deletions, it seems to be a hard problem, but we don't seem to have any techniques to prove lower bounds. Okay? Or maybe we do, we just worked, so that paper that I was just summarizing over the previous 2 slides hasn't yet been presented at a conference, but will be later this month. So that's pretty hot off the press, and I don't know if any of the lessons from that paper are applicable here. Of course, I've thought about it. I don't see how to do it yet, but one of you may be cleverer than me, so you can do it. And then the other thing is this model of adversarial robustness was meant to say safeguard against this feedback loop thing that happens when future inputs to an algorithm depend on past outputs. Okay, but in designing these algorithms, we assume that we have an all-powerful adversary who is really actively trying to foil the algorithm. Maybe that's too much, and maybe the real world doesn't quite operate that way. So what if the adversary itself is kind of limited? Maybe the adversary themselves has to be streaming, right? So maybe you are running a streaming algorithm and you're producing outputs, but an adversary who is himself a streaming algorithm can then look at your outputs and feed new inputs. Okay, so the adversary does not have infinite memory anymore. Now does this allow you more power? So now can you design algorithms for things for which we did not know algorithms before? So this, I think, is the other interesting question. Okay, so this third one, I guess, is what I was telling you, that the techniques we developed for MIF, maybe they're applicable elsewhere, and it remains for somebody to find that. Okay, thank you for your attention. I'll stop here.
Thanks a lot, sir, for an informative talk. Please feel free to ask questions if any.
2, 3, yeah. Oh yeah, yeah. It is. It is exactly. That's exactly the right term. So the Johns. Okay, good. So the Johnson-Lennard-Strauss lemma basically says that this matrix over here, if the entries are IID Gaussian, then IID normal variables, then it will have this property that I was saying here, right? So this lemma can be thought of as basically being a simplification of the Johnson-Lennard-Strauss lemma, or simplification or a variant of the Johnson-Lennard-Strauss lemma, which says even plus minus 1 entries will work. Yeah. Actually, there is an even further simplification which has been only hinted at over here, right? So when I said that you can generate them from a short random seed, the net effect of doing this generation from a short random seed is that the matrix entries, so they'll still be plus minus 1, but they will no longer be IID. So there'll be some dependence between the columns. And so that's a stronger result, saying that even not fully random matrices will have this property of being a useful dimension reduction matrix. Yeah. So good, thanks. There was something. Yeah.
Could you go to the slide where you mentioned the different random?
Oh yeah. This. Yeah.
So why should some random, like why should, let's say, random tape be more powerful than random seed algorithm? Because if for some realization both the random seed and random tape produce the same outcome,
Yeah.
the algorithm will give the same output.
Okay, okay. So when I say more powerful, I mean that something that requires this much space using random seed might require less than that space using random tape. So what is the extra power of random tape? That it gets to use more random coins than the random seed algorithm. That's all.
Where are the extra random coins being used?
Oh, I mean, I guess I did not give you an actual example of a random tape algorithm. So you haven't seen how to use it, but
Because in the illustration, it seems like in the random seed, all the coins are tossed beforehand.
that's right.
And in the random tape, every time you need to make a decision, you toss a coin.
Yes.
So effectively, it's the same number.
No, no, not that you have to toss a coin. You get to toss a coin. I think that's the right way to look at it. Because you could choose to, yeah, think of it this way. So you have your stream length, which is say m, and then you have your space, which is s, which is much less than m. Okay. So in the random seed case, you can use at most s random bits because you have to run in s space ultimately. In both cases, you have to run in s space. In the random tape case, you actually get to use m random bits because you get to use some fresh random bits with every stream item, but you will not get to remember them all. That's the thing. So if you toss random coins on stream item number 1, by the time stream item number 28 comes along, you've forgotten what random coins you tossed in stream item number 1, right? If you want to remember them and reuse them, then you have to store them and then you have to pay for it towards your space. So you can only store a limited amount, but you get to use fresh randomness with each coin, with each stream item. Yeah, I mean, without seeing an actual example of such an algorithm, maybe it's a bit hard to understand how this helps, but are you convinced that it might help? Yeah.
But after the decision has already been made,
Yeah.
there's no point in remembering it.
No, that's not true. So sometimes, okay, good. So sometimes when you see a stream item, what you do with the stream item might depend on what random decision you made like 28 items ago. It's conceivable, and there are algorithms that work this way. I mean, the easiest thing I can tell you is, do you know what Morris counter is? Because if you know, then that's a good example of a random tape algorithm. So what this is, well, I guess you can look it up later. This is a classic algorithm from the 70s or so, which maintains the approximate number of items seen so far. So if you think of it as you're just reading a stream, and I don't really care about what the items are, I just want to know how many items have arrived in the stream. So of course, an ordinary counter to count up to n will require log n bits. But Morris shows that you can do an approximate count with log n bits. So this is actually a classic. It is deployed. It is literally deployed in Google. They use Morris counters all over the place for summarizing lengths of various streams. But yeah, you have to know how the Morris counter works, and then you'll see where this random tape.
In the random tape algorithms, we are allowed to use fresh randomness of the order
Correct, correct. So you can toss random coins, make a random decision, but after that the coins are gone. So when the next item comes, you have a fresh set of random coins independent of the previous random coin. Yes. Yeah. Now, if you did want to correlate your current decisions to a past decision, which as I'm saying, sometimes you do want to do that. If you did want to have such a correlation, you have to go about remembering the past random decision, and then it counts towards your storage. You can't store all m of them, clearly. You have to be judicious in which ones you store. But good, yeah.
Any more questions? Okay. So we have arranged the refreshments at the coffee hut. Feel free to continue your discussions at there. Thank you all and have a great evening.
All right, thanks for coming. Yeah, I know.
I didn't expect it would be really this bad. So last time when we shifted the systems, it was working really fine.